Okay, Ian.
Okay, well, thank you very much for having me virtually here to give this talk to everyone. So the subject of this talk is kind of like around this very general but very natural question, which is, okay, so we're all interested in automorphic forms, but like how many are there? Okay, so obviously if you pose a question like this, you need to pick some sort of like invariant by which to count automorphic forms, because the trivial answer is there's infinitely many automorphic forms, which is not very interesting answer. So my perspective at least comes from like studying L functions. And so Sarnak has repeatedly kind of emphasized the important or the idea of using the analytic conductor to put an ordering on automorphic forms, which is kind of an invariant that comes out of studying L functions. And this kind of displays height-like properties. So the idea here is we want to try to make sense of what it means to order automorphic forms by analytic conductor and try to give some sort of answers to this question. So I'll explain what all that means in more detail. So I just wanted to start kind of like with just like really kind of classical examples of like, what do I mean by the analytic conductor in some cases that I think we all probably understand. So the first case is just the simplest possible case of automorphic forms you can talk about, which would be like automorphic forms on GL1 over the rationals. Okay, so in the kind of more automorphic world, I mean like group homomorphisms from this Idel class group to the complex numbers. But in an even more classical way, what I'm literally counting here is pairs that consist of a primitive Dirichlet character chi, along with an Archimedean character. Say this is like a function on the natural numbers, where t is a fixed real number, and so this is this is a character. Okay, so you can show that. Okay, so this is kind of like maybe a classical description of the set of like automorphic characters, if you will, on GL1 over Q. So I just wanted to describe in classical terms what I mean by this analytic conductor. So here, capital C of chi is going to be what I mean by the analytic conductor. And so here it's good. So first of all, it's a local invariant. Okay, so it depends on there's an infinite component and a finite component. So the infinite component C only depends on this Archimedean part here of this character, and the definition is that it's just like the conductor of this Archimedean character is just 1 plus the absolute value of t. And then for the primitive Dirichlet character part, or the finite part of this character, I just take this to be the modulus of chi naught. Okay, and then the analytic conductor is a product of these two things. So that's the story for GL1. And then I should describe maybe just like GL2 over the rationals, kind of the classical situation of holomorphic modular forms. What do I mean by this analytic conductor? Well, if F is a holomorphic new form on gamma naught of Q of weight K, then similarly this analytic conductor has a Archimedean part and a non-Archimedean part. So because I assumed it was a new form, so that's to say that like gamma naught of Q is the largest of the gamma naught groups for which F is modular. Oh, this should have said cuspidal. So let me just write that in. Is okay, so cuspidal. So this analytic conductor of this holomorphic cuspidal new form for gamma naught of Q. So the finite part of this analytic conductor is maybe what we would just usually call the conductor of F, which is to say it's the kind of the minimal Q such that F is modular for this group. And then the Archimedean part of this analytic conductor is defined in terms of the Archimedean local L factor. So here, okay, here's what the Archimedean local L factor for F, a holomorphic cusp form for gamma naught of Q looks like. So Okay, it's given by a product of these two gamma functions. And if it's weight k, then the arguments of the gamma functions are shifted by k minus 1 over 2 and k plus 1 over 2. So that the Archimedean conductor is these shifts plus 1, and it's a product of those two things. So this is roughly size kappa squared. Okay. And then similarly, if you had like if F was instead a Heck-Moss cuspidal Heck-Moss new form, you would have with, let's see, if in this case, if F has Laplace eigenvalue 1/4 plus R squared, then okay, and I guess frac A here is just equal to 1 if F is odd and 0 if even. Then this is what this Archimedean factor looks like, because these arguments inside the absolute values here would be like the shifts in the gamma factors for the Archimedean part of the L function. So at least now in these kind of two pretty kind of classical situations, you have an idea of what I mean by the analytic conductor. So in general, kind of for these classical ones, I'll use it a capital C to denote this analytic conductor. So are there any questions about this kind of classical situation up to this point? Okay. So the goal here is to kind of like address this question in some greater level of generality. So once you get away from, so for GLN, there's a pretty good notion of like finite conductor, because we have these nice kind of congruent subgroups. Like for GL2, we have these gamma naught congruent subgroups that define this, the non-Archimedean part of the conductor at least. And so there's a generalization of that for GLN, but once you get away from GLN, it's not so clear what the connection between a sequence of subgroups of GLN and the conductor should be. So for GLN, it comes through something called a new form theory. And these new form theories only exist for a few kind of very special groups. So we have them for GLN and like GSP4 and U3, but then there's only beyond that sort of like, very partial results. So this question is kind of like, okay, so it's even interesting for us to talk about what do we even mean by this question? What do I even mean by the analytic conductor in these more general situations? So I think like any kind of like whatever the correct setup for this question should be, it's got to be kind of consistent and compatible with the like Langlands functoriality conjectures and the local Langlands correspondence. So that's kind of, I think, okay, that's if you're going to like pose the right question, it has to be compatible with that at least. So if I'm going to define L functions, I need an extra piece of data in addition to like an automorphic form. I need a representation of the L group of this group in question. So here, G is like a reductive algebraic group, and there's some complex group that you can define out of it that I'll kind of say what it is concretely for a torus later in the talk. But this extra piece of information you need is a representation of this complex group called the L group of G. Okay, so then if you have that piece of information, then the local Langlands correspondence predicts the existence of some maps. So this thing here is the local unitary dual. So it's like the like KV points if say we're like, K is a number field. Say we're working over a number field K, and then this is the completion at V. So this AV of G is the local unitary dual of the group of local points of G. Okay, so this like very incomplete thing, but okay, we know a lot about the local Langlands correspondence by this point, but it's still parts of it, a lot of it is still conjectural. Predicts the existence of kind of these transfer maps from representations on these local unitary duals to representations on the local unitary dual of GLM. So the idea now is because this analytic conductor is a local invariant, the idea is to use this transfer map to just pull back the notion of analytic conductor from GLM to whatever group I'm working on. So in general, like the Langlands L function associated with automorphic representation pi and this representation R of the L group is a product of local factors where this R lower star V is this transfer map. So pi V is something in here, and then this is now on GLM. So then I have a standard notion of L function or local L factor on GLM, and then I just take the product. And so similarly, I have kind of like, I have a standard notion of local analytic conductor on GLM. And here I'm just going to take, I'm just going to pull back my representations on whatever other group. I'm going to pull them back to, or push them to GLM and then just take the analytic conductors there. Okay, so that's kind of like the general picture. And I'll kind of say more specifically what this means in details for a torus. But that's kind of the general conception of what I think, how to set up this question in this kind of like vast generality. Okay, so what's kind of known about this problem of counting by analytic conductor? So there's like not very many, there's not very many results. So we do have, so there's kind of like, there's an important paper of Brumley and Milosevic. So over a number field, for an arbitrary number field K, they can count the number of, so 0 here means cusp forms. So this is the cuspidal automorphic representations of GL2 over a number field. And this is C of pi is just like this standard notion of analytic conductor for GL2. And so these are going to be considered up to determinants of the IT twists. So that's kind of like saying, like if you're used to L functions, I'm only going to like kind of count the L function each kind of, I'm not going to count like vertical shifts of the L function. Okay, we can all like kind of normalize them so that all of those kind of like vertical shifts of the same L function count as one thing to count. So which I think is like a standard way to count in this universe of file laws. And so they get an asymptotic formula for this counting by analytic conductor. And it's like K is some constant, so it's like constant times Q cubed is the answer. So I mean, okay, this is like a really big work that they did, and they have a really beautiful kind of like interpretation of this leading constant K in terms of Plancherel volumes and Tamagawa measures, which is like, so it's like, it kind of fits into a nice kind of general framework of like what you should expect leading term constants for like arithmetic counting problems to be, but that's the subject of a different talk, and I won't really go there. They only save a single logarithm off the main term here, which is like a very small saving, but nonetheless, that seems like, okay, so that seems like a hard problem at this point to do better than log Q. Okay, this is still kind of really fresh, so maybe I won't say it's a hard problem, but okay, I don't know. So I think it's not so clear how to do better than 1 log Q here. I think it's maybe an interesting problem to try to improve this to power saving, but okay, that's a different part of the talk. So they also, or a different talk. So they also do GLN in general, but only under some sort of like additional kind of like either assuming some additional conjecture or only counting some part of the automorphic spectrum of GLN. And then there's like just a few other kind of results in kind of limited cases. So I guess like I started this thinking about this like a very long time ago, and I tried to find like the simplest case of a group other than GLN that I could tackle. So I did something extremely simple, and I just tried to count like characters on a one-dimensional non-split torus over Q. So this was something that kind of was done a long time ago. There's results of Didier Lesève, where he, okay, this kind of follows okay, so this situation of G is the units in a quaternion algebra over a number field is sort of similar in many ways to this, but so that's another interesting case of this question. And then sort of after doing this, okay, so I thought I could generalize it, and then it ended up being a big project, but I ended up eventually being able to generalize it to an arbitrary torus and a general representation of the L group, and then also a general number field K. So this is the result that I'm going to talk about today, and I'm going to try to. Okay, so I'll talk about this and kind of maybe so that the preceding discussion was a bit vague about what all these objects are, but I'll try to like make it all very kind of I'll make it all precise for this specific case of a torus in the following. So I think it's like a very kind of natural problem, and I don't know. There's still there's still a lot that's not known about this. Like in general, we don't even have any sort of conjecture about what the right asymptotic count should be for like in any sort of like generality, right? So okay, so are there any kind of questions about this introductory part up to here? Okay, so let me now kind of give some specific background about tori. So I'm going to get a little bit more technical now. So just to like, because maybe not everybody has worked with this before, so just want to kind of start from the basic definition. So what do I mean by a torus? So you can think about this as like somehow a commutative subgroup of an algebraic group. But so okay, but the definition is it's an algebraic K group is called a torus if so if I base change up to if there's a finite extension of the base field such that when I take my group and I base change it up to K, it splits as a product of n copies of GM. Okay, so these are fairly simple commutative groups. All my like automorphic representations here are just going to be characters, but nonetheless, the problem still gets like pretty complicated at this level of generality. So I need a few objects. So if this already splits over some extension, I can always assume I can take like K, capital K to be the minimal Galois extension, which splits the torus. And G now is going to be the Galois group of this extension splitting the torus. And I'm going to have so this is the character lattice of T, the algebraic character lattice of T. So I'm just going to take all the algebraic homomorphisms or morphisms from T into GM. So this is an abelian group, and it is like n isomorphic to n copies of Z. You can also take the co-character lattice, which is the maps from GM into T, and that's also isomorphic to n copies of Z. But the thing is, so what's there's more structure than these things just being like free abelian groups. So they also both admit actions of G. So G, the Galois group acts on both the character lattice and the co-character lattice. Okay. And so G also acts, okay, so this, so you can really kind of understand this as just, okay, so there's these, yeah, okay, free abelian groups with an action of this finite Galois group on them. And I'm also going to use a lot the algebraic, sorry, not the algebraic, the complex dual torus. So you can think about this as just being like the character lattice, like tensored up to C cross, or it can be the homomorphisms from the co-character lattice into C cross. Okay, so that's my complex dual torus. So I mentioned this L group before, and I started talking about representations of the L group, but in the case of a torus, I have this really concrete thing. The L group is just this semi-direct product of this T hat with this Galois group. So so this thing is always going to be isomorphic to C cross to the N. Just like these two things are like copies of Z to the N. So this L group is just like this very simple group with an action of a finite group on it. Okay, semi-direct product by a finite group. Okay, so that's what I mean by the L group. Okay, so now if I'm going to tell you what these conductors are, I have to use a bit of class field theory to tell you like what it is for like a general representation of this semi-direct product, this L group. Okay. Right, so I want to say like what this analytic conductor that I'm counting by is. So like I said, this thing is a local invariant. And I'm not really going to talk about the Archimedean case for the time being. I'm going to focus on like the non-Archimedean, the finite places. So now I'm going to switch to like local notation. So now instead of, so K here, oops, K was a number field in this line, and this is the Adele group of that number field. But starting here, F is now a non-Archimedean local field. So it's like one of the completions of K at some finite place. Okay, so I'm going to switch to L over F is my Galois extension splitting the torus. And I'm working now over a non-Archimedean local field. So we need the Ve group. So this is kind of like, this is a group that you can kind of think of as being very closely related to the absolute Galois group of F. So it's actually a dense subgroup, and it's all the like, it's basically like the elements here where you have like integer powers of Frobenius instead of taking like limits of those powers of Frobenius. But you can think of these as kind of like being some sort of Galois automorphisms. So I also need something called the relative Ve group. So that's this group here, W sub L over F. And this is the definition right here of W sub L over F. So what is this denominator here? This is the commutator subgroup. This is the subgroup of commutators of WF. So if I like had WF instead of WL in the denominator here, that would be just the abelianization of WL. So this thing kind of looks like if I take like F and extend up to L, and then I go all the way up to like the maximal abelian extension. This kind of group is like the Galois group of F all the way up to L abelianization, or the maximal abelian extension of L. So this relative Ve group is sitting in this short exact sequence. So here, this Artin map of class field theory says that these two things are isomorphic. The WL abelianization is isomorphic to L cross by the Artin map. And so then this map here in the short exact sequence is just you go up here and then you include inside WL over F. And then this thing also has a projection down to just the Galois group of L over F just by kind of Galois theory. Okay, so this thing is sort of like, I don't know, it's kind of like a fibered group with over this finite set where all the fibers look like copies of L cross. Okay, so that's what this WL over F looks like. So I also need to say what, so I need to invoke Langlands parameters. So a Langlands parameter is a map phi from this relative Ve group to the L group of my torus, which is just, remember, this is like C crossed to the N semi-direct product of finite group. And I need to have just these maps that make this diagram commute, where sigma here is this map sigma. And then this map is just the projection map where G is like G is here. So out of the semi-direct product, I always have like, I can always just restrict to the G component. Okay, so I have to have this diagram commuting for this to be a Langlands parameter, and these are, okay, and then I actually have just each of one of these Langlands parameters is actually a conjugacy class up to T hat conjugacy. So those are my Langlands parameters. So now capital phi of T is going to be the set of Langlands parameters of T up to T hat conjugation. And so what does the local Langlands correspondence for tori say? So this is, by the way, this is like actually like a theorem of Langlands himself from like the 60s. I think it was like finally written up at some point, but it was sort of done a very long time ago. So he says there's the canonical bijection from, so these are the F points of the torus. So these are characters chi of my torus to Langlands parameters phi. Okay, so that's kind of right. Okay, so that was the local Langlands correspondence in this situation. So then how am I going to define this local L function and the conductor? Well, I'm going to you take the local Artin L function of a complex Galois representation. So I need a complex Galois representation, and this is how I get it. I take my Langlands parameter, which let's just remember that Langlands parameter is a map from WL over F to LT. And I'm just going to compose that with the representation of the L group. And then that gives me, remember this thing is like a Galois group, and this gives me a complex Galois representation. So I take yeah, okay, so that's how I attach a complex Galois representation to a character and a representation of the L group R. So then finally, the local L function is defined like this. So I have this complex Galois representation, and I take the Frobenius element here, and then I get an M by M complex matrix, and then I take the determinant of the identity, the M fold, the M by M identity matrix minus this other matrix. Okay, so then that's my local L factor. And then this is the definition of this non-Archimedean local analytic conductor, is just I'm going to take it to be the okay, so it's you pulled you compose, okay, so it's okay, the conductor of this complex Galois representation, and here QF is the cardinality of the residue field of F. Yeah, and then A is this like Artin conductor. So here is kind of like one definition of the Artin conductor of V, a complex Galois representation. So it's in terms of these groups G upper I. So this is the upper number, like the upper numbering filtration of the Galois group that splits the or the Galois group, which that you're taking the representation of. So this is actually going to be WL over F in this context, and this is the upper numbering filtration, and you take this codimension of the fixed points in V. This is going to go to 0 eventually, so this is actually just a finite integral, but okay, that's one definition of this Artin conductor. So really what I'm doing is I'm going through the local Langlands correspondence, and then I'm taking the Artin conductor from the Galois side of the local Langlands correspondence. And also the L function from the Galois side of the local Langlands correspondence. And that's how, for the case of tori, I'm going to define these local analytic conductors for the non-Archimedean places. Okay, so here's just like a simple example of what I'm doing. Because that was all, I don't know. Okay, that was a lot of stuff. So let's just take like the simplest possible example. If my T is just GM, okay, the simplest torus in the world. So then the Galois group splitting the torus is trivial. This is already a split torus. So this semi-direct product is the empty semi-direct product. It's just a copy of T hat, and that's just C cross. Okay, and then for instance, I can take R to be this representation of the L group. I'm just going to take a complex, non-zero complex number and send it to this diagonal matrix. So A, B, and C are just going to be some integers. I guess I didn't say that, but here A, B, and C are just going to be in some integers. Okay, so I can just pick whatever integers I want, and then this gives me a 3 by 3 matrix. It's a three-dimensional. Okay, it's very reducible, right? It's just a sum of 3 one-dimensional pieces, but nonetheless, here's a representation of the L group you can pick. And in this very simple situation, the Langlands L function attached to these data is just like the Dirichlet L function of each of these characters, chi to the A, chi to the B, and chi to the C. Okay, and then the analytic conductor with respect to this representation R is going to be the analytic conductor of each of these 3 characters. Okay, this is what I mean by this capital C of a Hecke character. Okay, there it is. Okay, so I should mention there's like some other kind of results. So there's some results on like looking at some analytic questions like moments of L-functions in this in this family of this toroidal family of automorphic characters. So I think there's one paper that they have out where they just take instead of a 3, they take 2, and they just have an A and a B, and they have an analytic study of moments of L-functions over this toroidal family, and they kind of like okay, so it leads to some interesting questions, and they bring in some so this gets related to like they bring in tools from algebraic geometry and like L-adic sheaves. Okay, so for bounding certain Kloosterman sums that come up in the computations of this. So already kind of in this simple situation, you're kind of having that some of these kind of questions we like to study as like people who work on analytic theory of automorphic forms start getting related to other interesting parts of mathematics here too. So, and then, so okay, so you can study other kind of like analytic questions about this family, and I have a graduate student right now working on some of these sorts of things. Okay, so that was all local, but maybe I should say what the global setup is that I'm talking about, because that example was global, but everything I said before about class field theory was local. So, I mean, what I wanted to know, so the question is, can like in this like vast level of generality with like an arbitrary torus and an arbitrary kind of splitting type and like an arbitrary representation of the L group, can you say anything at all at this kind of level of generality? So maybe I should say what the global setup is. So here now on this, like K is going to be a number field. And by the set of automorphic characters, which I denote script A of T, what I mean is I take this automorphic quotient. So here, this is the K Adels. And you, okay, look at this automorphic quotient, and you're going to look at, so an automorphic character is going to be a continuous unitary character of this automorphic quotient. So this A of T is it's a locally compact Hausdorff abelian group. So I can just choose a Haar measure on it, and all of these are related up to a constant. Okay. So then the general kind of global definition here is I'm going to take chi and I'm going to write it as a product of finite characters. And then I'm going to go by the local Langlands correspondence at each place, and I'm going to get a Langlands parameter. And then I'm going to take the local, these local analytic conductors, and I'm going to take a product of all of them, and that's going to give me my global analytic conductor. And so now a more precise version of this question that I had on the first slide is what's going to be the growth rate of the set of characters in this set with this exactly this notion of analytic conductor, which I defined on the previous few slides, being bounded by X, say. And I'm going to count that by the Haar measure that I've picked on this A of T. So this set A of T is, it's the way I've defined it here, it's not a discrete set, but it's like close to a discrete set. It's like a discrete set cross R. So here, really, you know, this, okay, I've said it in terms of Haar measure, but really this is kind of like some, this Haar measure is not some like complicated thing. It's really just kind of like counting measure across Lebesgue measure on each of these copies of R. Okay, so the question is, what's the volume of this sort of thing as X is running to infinity? So maybe I should pause and see if there's any questions about like just the setup of this question that I'm going to try to answer now for Horace. Okay, so to state precisely what the answer is, I need a few more definitions. So I have R, and remember R is a representation of this semi-direct product with the Galois group to GLMC. So now if I take this R and I just restrict it to T hat, this M-dimensional representation is going to break up as into one-dimensional pieces because T hat is just a C cross to the N. And so it has this like co-weight space decomposition for, oh, sorry, there's a small typo here. This should be, but I can fix it. That should be a hat there on that T. So here I have some characters of T hat, and I have the V is like the space of, V is the space of R. Oh, so V is C to the M in this case. And this V sub mu is the subspace of CM where R acts through the character mu. Okay, so then here's something kind of like, this is kind of important for all the following definitions. So I'm going to let M be the multi-set of mu's that appear in this co-weight space decomposition. Okay, so they might come with multiplicity equal to the dimension of the space where R acts through mu. Okay, so but it's going to be the set of mu that show up here with this multiplicity. Okay, so then there's these complex groups, these complex commutative groups that show up that turn out to play, okay, tell me what the answers are. So S is going to be a subset of these this set of co-weights, and then DS is this is like a complex diagonalizable group. So that's to say this is like a number of copies of C cross times like a finite group of roots of unity. Okay, so it's going to be just like the intersection of a bunch of mu's. So remember the mu's are characters of T hat. So this intersection of kernels is sitting inside T hat, and I'm taking the complement. So here SC is just like, it's M delete S. It's the complement of S in M. And I run over all the mu that are not in S, and I take the kernel of each of those mu's and I intersect them together. So I wanted this to be like covariant in S. So this D of S is small if S is like the empty set and is large if S is like the whole set M. And that just came out naturally out of the computation also. Okay, so here A, this is going to be like the power of X in the answer to this counting question. And so what I do is I look at all the subsets of M. I throw out the ones where this D of S is the trivial group. So in particular, so this, maybe the set is like infinity or not well defined if R restricted to T hat's not faithful. Because if that's not faithful, then D of the empty set is going to be not equal to 1. And so, but then that gets excluded by this condition if it is faithful. Okay, so then I just, so this kind of, the denominator is not 0 because thanks to this, if my representation is faithful, and I just compute the dimension of this complex group plus 1 and divide by the cardinality of the set S. So I have a finite set of these rational numbers, and I just take the largest one, and that's the definition of A. And then, so the theorem is that, so if this R is a faithful representation of the L group, then there's some polynomial so that the size of, okay, so that the Haar measure of the automorphic characters with this notion of analytic conductor less than X has this sort of asymptotic formula. So A is the constant I defined in the previous slide. And the power of X that appears is A, and then it's times a polynomial in log X. And on the other hand, like if R is not faithful, then this A is either not defined or it's infinity. And so in that case, the left-hand side here is actually infinite for some finite X. So fine. So you need really R being faithful is like the right condition for this to be a well-posed problem, for it not to be like infinity at some finite point. Okay, so that's one kind of the first version of the theorem. So I can also say what the degree of this polynomial P is, but that kind of requires a few more definitions. Or maybe, let's see. Yeah, okay, fine. So, are there any questions about the result or what I'm doing or what the anything is here? Right.
What's the error in this asymptotic?
Yeah, good question. So if uh maybe I can answer that question towards the end. So let's say, okay, I'll tell you quickly the answer, and then maybe the answer will make more sense later, and then we'll come back to it. But so the error is something, it looks kind of like the error term in the prime number theorem. So it's like if you assume the classical zero-free region, it's like e exponential of minus a constant square root of log. Or something slightly better based on the Vinogradov-Korobov zero-free region for Hecke L functions. If you're willing to assume the Artin conjecture for Artin L functions, that's to say that the L function of an Artin L functions are entire except for like one pole at the edge of the critical strip, then you get that. If you assume the Artin conjecture, then you get a power saving error term here in X.
Okay.
Yeah. So I'll come back to that. I'll say why that is if I have time to go through the proof.
Okay, thanks.
Sure.
Is there a formula for the leading term of this polynomial?
So I don't have any sort of nice formula for the leading term of this polynomial. So again, I'll show you, I'll say why that is if I have some time to go through the proof. So it's a theorem, right? So the method produces some expression for the leading term, but that expression will be like horrible. And it'll just be in terms of a bunch of like awful infinite sums and integrals that I can prove converge, and it's like some mess, but like I wouldn't say it's like interpretable. Like it's not like Brumley-Milosevic's constant where they have like a very nice interpretation of this constant. So the theorem doesn't produce any nice constant for this, but I think that would be like an interesting direction to keep working on. Yeah, because there's like this whole, okay, so this whole story has like a nice analog with Manin's conjecture for the number of rational points of bounded height on an algebraic variety. And in that case, there's really nice conjectures for the leading term constant due to Emmanuel Petrow and others interpreting those as like adelic volumes also. So I would love to have the same kind of conjecture for the leading term constant here. And okay, so Brumley and Milosevic have thought about this, what the answer kind of like should be also. But right now, like my method is not getting anywhere close to having a nice expression like that. But that's certainly something to think about. Any other questions? Okay, but I can at least say that the next thing you might want to know after what the value of A is, I can say what the degree of this polynomial is, but I have to give a few more kind of combinatorial definitions. Okay, so right, so let's remember what M is. M is the set of co-weights. So maybe I should just go back and quickly recall to you. So I take R and I restrict it to this commutative group, and then I get these co-weights mu, and M is the set of co-weights. Okay, everything happens in terms of this set of co-weights. So sigma, I'm going to be the set of S, the subsets of M that attain A. So A was like the max of all the fractions like this over all subsets of M, and then I'm just going to let sigma be the S that actually attain A. Okay, that are non-zero. So I have to enlarge this set a little bit. So I'm going to call the enlargement sigma tilde. So this is kind of like a fibered set, and the base of this fibered set is sigma, and the fiber over S, which is a point in the base, is the number of is the group of connected components. So pi naught is the group of connected components of this complex group D of S. So remember, this D of S was here's D of S. It's a number of copies of C cross times a group of roots of unity. Okay, so it's just saying take the group of roots of unity of this DS. Okay, so then I have okay, this is a group of pairs, and you can think of it as the base sigma, and then the fibers are all the connected components of D of S. Okay, so G, this Galois group, is acting on the complex dual torus. So it acts on the set of coeights. And then it also acts on the set of subsets of the coeights. So the S's get moved around by Galois. And the Galois action preserves the dimension of this complex group ds. So actually G is acting on, maybe I should draw it over here. Okay, so Galois group G actually acts on sigma. But I actually need to, okay, so now I need to enlarge the Galois group a bit to get it to act, to get the right action on the enlarged sigma. Okay, so I need a new number. So lambda is just the LCM over all the component groups of all the D of S's. The groups of connected components of all the D of S's. And so what I'm going to do is I'm going to take this. Okay, so remember G is Galois of K over K. And I'm going to join the lambda roots of unity to K, and then look at this Galois group. Okay, so this is going to be my enlarged Galois group. This sits as a subgroup of G cross this finite group. Okay, where this part acts by just like taking powers of this root of unity. Okay, so then if I have a pair G comma gamma with G sitting in G and gamma being in here, that's going to act on sigma tilde by just like moving, so it moves S and the connected component by G, and then it takes the gamma power of the connected component. Okay, because this is a group and you can, okay, so this raises those to powers and moves them around within that one group of connected components. Okay, so then, also this G tilde also acts on this sigma naught tilde. Okay, so this sigma naught tilde is just like the sigma tilde delete something. That part's not important. But I have to tell you the truth. Okay, so finally, the result is that the degree of the polynomial in log x is the set of orbits, the cardinality of the set of orbits of these two objects that I just defined, -1. Okay, so I just take the number of orbits for this action and subtract 1, and that's the degree of P. Okay, so there you have it. So okay, I don't really have too much time to go into it, but there's kind of, again here, a nice analogy with Manin's conjecture on the number of rational points of bounded height on a variety. So like in that case, you can like you choose like a line bundle. You choose an ample line bundle to take your projective variety and embed it in Pn. And then you can take the naive height from Pn and pull it back to your variety. So that's just like that choice of line bundle is like the choice of this representation of the L group. Okay, and then somehow when you're doing the like conjecture in for Manin's conjecture has to do with like okay, some sort of maximally defined thing. You like look along a line through this ample cone or something like that, and you take like a maximal point on that, which is like very similar to, okay, I have this thing and I'm taking like the max of this combinatorial object. And then also here, like the number of orbits. So somehow this like vaguely looks similar to something Manin conjecture-esque. Okay, so let's do an example since this is all like a lot of notation. So again, let's just take T as like the most basic torus in the world. So we already saw that the L group is just C cross and the Galois group is trivial. So if I just take two coprime integers A and B, and I look at this representation of the L group, if these are coprime, then this is a faithful representation of the L group. And the analytic conductor in this case is just, you take the classical notion of conductor for chi to the A and chi to the B. So that's, and I want to do the counting problem in this situation. Okay, so here's all this data that I just talked about in the previous few slides, like written out in a concrete example. So let's just take A is 2 and B is 3, which are two coprime integers. So the set of coeights is just the the characters of C cross given by Z squared and Z cubed. And then here's all the subsets of this set of cardinality 2, the empty set, the first one, the second one, and the whole thing. And then what do I do to compute D? I look at the complement. So maybe it helps to look at this one first. So the complement is just Z cubed. And then the kernel of that is the third roots of unity. And conversely, if I take S as this, I take the complement of that, which is Z2, and then the kernel of that is plus the second roots of unity. And if I intersect these two things, I get nothing. And if the complement here is like the empty set, so I should take the whole of T hat. Okay, so there's my list of groups DS for the different S's. And so then if you look at this, okay, this condition says you exclude this. So I have these three things to compute, and then this ratio is 1 for all of 3 of those things. Okay, so that says that this constant A is equal to 1. Okay. So now if the Galois group might be trivial, but this extended Galois group is now Z mod 6 Z cross. Okay, I'm confusing whether I'm speaking British or American English now. I'm sorry. So maybe I'll revert to my roots and say Z. So Z mod 6 Z cross. Okay, that's this like extended Galois group now. And remember, sigma was the set of S's that attain A. So that's all 3 of these things, all 3 S's. And sigma, or the extended Galois group doesn't act on that, but it acts on this extended set, sigma tilde. So here, okay, my 3 base points are here, and then here's the next one, then here's the third one. And then this one, Z2, has that component group sitting over it, so I have each of the third roots of unity. And Z3 has this component group sitting over it, so I have the second roots of unity. And then this one has a trivial component group, so I just get 1. Okay, this sigma tilde 0 said I delete some stuff in the previous one, but okay, whatever. So that's the deleted, that's after deleting some things, I get those 3 objects. And then finally, this, okay, this just consists of the integers 1 and 5, right? So I take from this previous set, this extended Galois group just acts by, okay, the non-trivial element, the 5, just acts by swapping these 2 components, and then it fixes these other 2. Okay, so how many orbits do I have? I have 1, 2, 3 orbits, and the upshot is that the size of this set is like some constant x log x squared. Is that okay? So that's a workout in this very simple example, what the theorem says. Okay, this example, it also jives with your kind of like a simpler explanation here. So if I'm counting by this conductor, kind of like all the contribution comes from either quadratic characters or cubic characters. Because if I have like a quadratic character, one of these is going to be trivial. And if I have a cubic character, the other one's going to be trivial. So those 2 kinds of characters are going to have particularly small conductors. And then just a generic character is going to have like a much bigger conductor because both of these will be large. So I'll get like the square of those previous 2 things. So this is basically, this family is like just kind of counting like how many characters are there that are either quadratic or cubic of conductor less than x. And so then this kind of makes sense as a answer if you think about it in those terms. Okay, so it passes the sniff test. Okay, so let me just stop here. I don't know. I have like what, 6 minutes left? Maybe I can just say a few words about the proof in 6 minutes.
Sure.
Okay. Okay, so here's like the first kind of structural steps of the proof. So one kind of important thing is that this problem is a very natural local to global structure. Okay, so as you could already see in like the definition of the conductor, it's a local invariant. So you can reduce pretty quickly to like a local problem. And if you're doing a counting problem, it's very natural to use generating series, as like our colleagues in combinatorics know. So here's the conductor zeta function. I have this set A of t, and it's got a Haar measure on it, so I can take integrals with respect to a Haar measure. And then I take 1 divided by this analytic conductor to the s power. So it looks like a Dirichlet series. And then we're well acquainted with how I extract the count out of a Dirichlet series using standard kind of techniques in complex analysis. So what I want is this z of s to converge absolutely for a real part of s bigger than a, where a is that constant, the max of this thing I defined. And I want it to have, we will be able to show that it has a pole of order the number of these orbits at s is equal to a. So that's really what the theorem says, is that this generating series has, okay, it converges absolutely here and I can identify exactly the order of the pole. What I can't say is what the residue of this pole at s equals a is. Okay, so like I said, I can show it has this pole and the residue exists, but I just like can't write down any nice formula for it. It's just something horrific, okay? So this thing looks like the Adele class group, right? So everything works in exactly the same way for tori. So it sits in this short exact sequence. So the quotient is this finite class group of T, and the kernel is okay. So it's a product over all the integer points over all the local fields of the torus, and then the field points of the Archimedean places, and quotiented out by the global units of the torus. So what I mean by the global units of the torus is this. So they're, okay, yeah, they're units at all finite places, and then they're also field points, number field points. Okay, so just like in algebraic number theory, there's a Dirichlet's units theorem here. This is like, it looks just like for a number field, it has a rank and then it has a finite component to this thing. Okay, so for if we were doing like Violon GLN, the main tool that's used here is the trace formula. So my version in here from the trace formula is to use Poisson summation. It's a commutative case. It's much simpler than using the full trace formula, but here's the use of the trace formula. So if I just apply Poisson summation to this generating series, what I get is that z of s is a sum over all the global units of the torus. So you can think of those as like the obstructions from local to global. Of like, there's one generating series for each global unit of the torus. But now the local, so now the generating series attached to this global unit factors over places. Okay, so it's like your orbital integral factors over into local orbital integrals. Okay, so here these are going to be the non-Archimedean ones, and here's the Archimedean ones. This is just a repeat of the previous slide, so you can keep looking at it. Okay, so what I care about is the location and the order of the rightmost pole of this for each global unit. So because it's a product over this infinite product, the location and order of that rightmost pole only depends on all but finitely many places. Because okay, it's just like if you looked at the Euler product for the zeta function, if I changed finitely many of the local factors, it might change the residue, but it won't change the location of the rightmost pole. So that's like one reason why I can't say what the leading constant is because I can get away with only looking at all but finitely many places if I only care about the location and order of the pole. So it suffices to just look at the V that are the places that are unramified in the splitting extension. And so in that case, okay, so there's already like a lot of work that goes into producing this formula for this local counting problem. And it's really using quite heavily that I'm at an unramified place, but basically this is what it is. It's, okay, yeah, so it looks very similar to the global thing, right? I'm just counting characters of the integer points of the torus. Okay, I switched to local notation, so F is now the non-Archimedean local field. And then I have this local analytic conductor to the S, so it looks very much like a Dirichlet series, and it's twisted by chi of X, where X is the global unit here, okay? So then the idea is, so this is on the automorphic side, and I'm going to pass to the Galois side now. Now I'm going to invoke the local Langlands correspondence for tori. Because after all, when I define the local these analytic conductors, I define them in terms of the Galois side. So it's completely natural now to pass to the Galois side. And all of my counting is going to happen on the Galois side instead of the automorphic side. So stating the local Langlands correspondence in the like cohomological version of it. What I said about Langlands parameters in the previous slide is just boils down to this, that this group of homomorphisms is like this H1 group cohomology of this relative A group into T hat. So kind of a key point is that if I restrict this homomorphism to the integer points, because I have to work with integer points here, this side of the local Langlands correspondence is just G equivariant homomorphisms from the, oops, oh my heavens. Is G equivariant homomorphism from the integer points of, or sorry, the units of L into T hat. So now this one like is much easier to work with group theoretically than this one, which is like one of the nice things that happens. So in that case, I can write NF. Here's writing it on the Galois side of the local Langlands correspondence. So I look at these C's, which are G equivariant homomorphisms from OL cross into T. And then here, these mu are these maps. These are these co-weights. So remember, they're maps from T hat into the complex numbers now. So this thing on the inside of C is really just like a complex valued character of OL cross. This C is the standard notion of conductor in terms of the standard filtration on OL cross here. And then I have a sum over all of these co-weights. So now already you can see the kind of connection between these local generating series and these like kind of like group theoretic gadgets in terms of subsets of M. So you can study this thing and for the unramified case, and you can pick out a main term here out of these sorts of things. So maybe I'll just stop with this slide about the outline of the steps to finish the proof. So there's a bunch more, okay, that's the general setup, and there's a bunch more things that you have to do. So even though you only care about finitely many places, you better have absolute convergence for each individual local factor past your pole. And already just doing that for like the Archimedean places is pretty non-trivial and is required for the rest of this. So I already talked about this part a lot, is compute for unramified V, compute these local series finally enough to have a kind of a group theoretic description for the leading term. And then maybe I'll just kind of focus on this part and then I'll stop, is if I take the product overall, like the good places, all but finitely many places of these local series, I can compute these close enough to be able to compare this to a finite product of Artin L-functions. And now at this point, you get the analytic continuation of the generating series using the Brouwer induction theorem. And because I have to use Brouwer induction theorem here, I can't exclude the possibility that these Artin L-functions have infinitely many poles inside the critical strip, which could come close to the edge of the critical strip. But I know like zero free regions for Hecke L-functions, so I have at least some zero free region of analytic continuation past the A line. And then you can continue, and then you're okay. Then you get your analytic continuation. And if I assume the Artin conjecture, then I would get analytic continuation all the way up to the center line of those Artin L-functions that I get here. Okay, and then I have to finally show that like the sum over the global units converges, and it does. So okay, I'm sorry I already ran 4 minutes over, but I'll stop here.
Thank you. Let me stop the recording.